Good day, Precal of STC and MedHigh. Still in Chapter 8. We are seeing the light at the end of the tunnel. I just hope that it's not a train. Finishing up applications of trigonometry. And we're in 8.6 right now. 8.6 piggybacks off of 8.5. If you remember 8.5, 8.5 we were looking at the graphical representation of complex numbers being treated as vectors with magnitude and direction. And so we even multiplied complex numbers together in trigonometric form, and we divided them also. This is related because what de Moivre's theorem does, de Moivre's theorem is really talking about raising something to a power. Raising your complex number 2 plus 5i to a power, but doing it in trigonometric form. I mean, sure, you could have done 2 plus 5i times 2 plus 5i times 2 plus 5i, and you could have foiled it, and you could have simplified it, but there's other representations for when it's in trigonometric form. And then we're also going to talk about, could you also take the square root of 2 plus 5i? Now, that would be difficult to do as complex numbers. But if you put them in trigonometric form, there actually is a process thanks to de Moivre. And it's a lot to chew on, but we'll get through this. Remember what we did. We found out this particular value here, what this representation meant. It started out by having like 1 plus 1i, and doing something with this to convert it into, if this was a vector, 1 to the right for this positive 1, and then that's a 1i, so up 1 for, this is your I, so it's up 1 here. So here's this vector here. And we would have to have found out what the angle is, and we would have to find out what the length of this was. So we would have dropped it down and realized that this is a 1, and this is a 1. That's a 1, 1, square root of 2 triangle, and you should know that was a 45-degree angle. So I found my theta. My theta is 45 degrees. Then to find out what the argument is, that means the length of this was, we would take the 1 and the 1, and we'd take the square root. This is what we're looking for, r. 1 squared plus 1 squared is going to be 1 plus 1 is 2, square root of 2. So we found out what r was. So r goes here, and then we say if our angle was 45 degrees, we can put square root of 2 cosine of 45 degrees plus the I always goes with the sine of the 45 degrees. So there was my trigonometric form. And to make it simpler, we write square root of 2 cis of 45 degrees. And it's still related. So this is just a complex number, just like 1 plus I was a complex number. And if n is any real number, if you were to take your complex number and raise it to a power, then the shortcut answer is r to the n. You take your r, raise it to the n, you take your n, you stick it next to each of the thetas. So if I was to do my 1 plus I to the 8th power, which I'm not interested at doing 1 plus I to the times 1 plus I, let me write that better. 1 plus I times 1 plus I times 1 plus I times 1 plus I, 1, 2, 3, 4, 5, 1 plus I, 6, 1 plus I, 7, one more, 1 plus I, and then start distributing, and then distribute, then distribute. It would take you forever. It's so much easier just saying the answer is going to be the 8 times square root of 2 times cosine of 8 times 45 plus I sine of 8 times 45, or simply 8 square roots of 2 cis of 8 times 45 degrees. That actually is easier. So there's my answer. And it would take me forever to do this. And then once you have this, we can do 8 times 45. How much is that? 8 times 45. Well, that's 360 degrees, isn't it? I think so. So 8 square roots of 2 cis of 360 degrees. Well, I can actually convert this back into rectangular, to the complex number. The same way I want my original answer to be. I would love it to be a plus bi, some answer when I get all done. So let's see. 8 square roots of 2 times cosine of 360 degrees plus an I times sine of 360 degrees. Cosine of 360 all the way around is a 1. Sine of 360 is a 0. So it's going to be 8 square roots of 2 times a 1 plus 0 I. Well, who writes that? 8 square roots of 2 is, you could write it 8 square roots of 2 times 1 plus 8 square roots of 2 times 0 I, and there's your a plus b I. Unfortunately, it turns back into just 8 square roots of 2 because this whole thing goes to 0. So this was amazing. I just found 1 plus I to the 8th power, and I found out that it was 8 square roots of 2. It's, to me, remarkable. But that's the shortcut. And so, I think, what did I do? Did I do it to you again? Remember we did with it? The r gets raised to a power, and each angle gets n to that power. So, page over here. Yeah, I wanted us to see if, instead of memorizing this rule, let's really do it. Let's do 1 plus I square root of 3 squared and see where it leads us. It turns into 1 plus I square root of 3 times 1 plus I square root of 3. And what I can do is, let's just, the old school. Let's FOIL it and see what happens. Now, granted, when I do this, it's going to still, this is called rectangular. Remember, it's still rectangular because we would graph it 1 to the right and then square root of 3 up. That's my I, and so there's my vector. So this is rectangular, okay? You're on the rectangular plane. So 1 times 1 is 1. 1 times I square root of 3 plus 1 times I square root of 3 is plus 2I square root of 3. I times I is a negative 1. Square root of 3 times square root of 3 is 3. So it's a negative 1 times 3, negative 3. 1 minus 3 is a negative 2 plus 2I square roots of 3 is my answer. Probably I would rewrite that to negative 2 plus 2 square roots of 3 I. Or if you like the I in front, you can do that. Whichever you want. So there's old school. And if I want it in trigonometric form, I would have to graph this, go 2 to the left, up 2 square roots of 3, which is, I don't know, it's got to be It's got to be less than 4. So it's up here somewhere. And then so this is a negative, this is -2, and this is 2 square roots of 3. That's going to be that distance there, 2 square roots of 3. You'd have to find out what this angle is, and you'd have to find out how long that is, and it's going to be a lot of work. Moving on here. Let's do it using my formula from the other day. I copied this from the last lesson, the product theorem. I know you already forgot it, even though you already did your homework. If you're multiplying 2, what you would have to do, well, you notice these are in trigonometric form. So we need to first convert this into trigonometric form. So 1 plus, we have to do the work. Well, I just did it. Or did I really do it? No, I didn't do it. Let's draw it. 1 over up square roots of 3, which is 1.7 something. There it is. Okay. This triangle then, that's a square root of 3, and that's a 1. There's my right angle. Okay, that looks to me like a 1 and the hypotenuse being a 2, and that's square root of 3. I've seen this before. That's a 60-degree angle. Theta is a 60-degree angle. I remember that triangle. Now I just got to find out the length, the magnitude of that vector. So r will be the square root of 1 plus 1, oh no, 1 plus 1 squared plus square root of 3 squared, which is a 3. So that's going to be r is equal to the square root of 1 plus 3, which is square root of 4, which is 2. So here's my vector. It is going to be, my r is 2 times cosine of 60 degrees. And guys, we should be doing radians as often as we can, but plus an I sine of 60 degrees. So there's the number he's talking about right here, okay? And if we were going to take this same number times itself, in other words, I'm taking this and I'm going to square it. Look what we do. When you square the 2, that becomes a 4. And then now that you have these two numbers, the rule said last time was you multiply, you add their when you're doing this. Why am I squaring it? That's what. Let's just leave it like 2 times 2 cosine of 60 degrees plus I sine of 60 degrees. Your shortcut from the last lesson was you do multiply the two numbers, the two r's. There it is, see? R1, R2. It just so happened that my two r's were the same. And then we were supposed to add the two angles together. So theta 1 plus theta 2, theta 1 plus theta 2. Well, let me look at what I have here. These are my thetas 2's, and these come from my theta 1's. So theta 1 was 60, so it's going to be cosine. I don't know why I wrote the whole word cosine. I didn't even write the E. Cosine of 60 plus 60 plus an I times sine of 60 plus 60. So it breaks down into 4 CIS of what? 120 degrees. Okay, so that was just squaring it. Now I'm just curious, if I leave it the way it was and say 4 cosine of 120 degrees plus an I times sine of 120 degrees, what would that become? Let's see, 120, where's that at? 60's here, 120's out here, there it is. Drop your triangle, let's see. That's a 60-degree reference, so that's a square root of 3. That's a negative 1. This is my 2. What's the cosine of this angle? Cosine is adjacent, it's a negative half. 4 times a negative half plus an I. What's the sine of this? Well, sine is opposite, square root of 3 over 2. I square root of 3 over 2. And then if I multiply through, let's see. 4 times a negative half is a negative 2 plus 4 divided by 2 is 2. 2I square root of 3. Does that look familiar? Negative 2 plus 2I square root of 3. It's the same answer I did when I did it old school by foiling it. And I admit, that was so much easier to do it just by taking my complex number and squaring it. But this took a lot of work. But again, why do we learn this problem? Is I don't really want to do I plus square root of 3 to the 8th power. I don't really want to do it. It would take a long time, as I said before, to expand it out and multiply it out. But with my new, well, we didn't come up with a secret yet for doing 8 of them. We have that shortcut where I take the r to the 8th, and we already found out that 1 plus square root of 3i was right here. So let me write that out. That was 2 times cosine of 60 plus I sine of 60. The formula we had on the other page, that gives me, if I'm doing all of this to the 8th power, it's 2 to the 8th cosine of 8 times 60 degrees plus I sine of 8 times 60 degrees. And we would just shorten that out to, what is 2 to the 8th? 2, 4, 8, 16, 32, 64, 256. 256 cosine of 8 times 6 is 480 degrees plus I sine of 480 degrees. And that's fine. This is my trigonometric form. I could turn it back into rectangular if I wanted to, have an a plus bi with no trig in it. We could do it. All right. I almost taught the whole lesson, really. Oh, I don't know why I have this here again. Okay. So here we are. Well, that looks familiar. I was doing another problem to the 8th power. I was doing 1 plus I to the 8th power. This is 1 plus I squared to 3 to the 8th power. We did play around with this on the previous page when I squared it, I believe. So I don't remember my answers. Let's write it. First of all, let's figure out what this vector looks like. 1, and that's a square root of 3 at the top, so it's a little bigger than, it's almost a 2. It's probably 1.7, something like that. And so my vector goes out to here. Drop my triangle. That distance is 1. That distance is square root of 3. So we know that This was the 1, 2, square root of 3 triangle. And so 1, 2, square root of 3, the legs being 1 and square root of 3 means this was the 60-degree angle. So I found out what theta was 60. And the r is 2. So in trigonometric form, which remember was r times the cosine of theta minus I sine of theta, or r cis of theta. So 2 cosine of 60 degrees minus I sine of 60 degrees, or 2 cis of 60 degrees. This is in trigonometric form. This is in that's a polar in rectangular form. There's no trig in that one, but I did write this part. I wrote it down here. That's this part right here. So that's my first step. Let's see. Do I finish it up on this screen or on the spot? So once I have my problem, do I finish up on this screen? Oh no. And okay, I wrote it. I want this to the 8th power. And the trick was 2 to the 8th. Oh, I sort of remember doing that. And I can write cosine of 8 times 60 plus I sine of 8 times 60. And 8 times 60 is 480. So 2 to the 8th, I think I found out was 256, wasn't it? 2, 4, 8, 16, 32, 64, 128, 256. Cosine of 480 degrees plus I times 480 degrees. So there's my answer in trigonometric form. And I don't know. Oh, he wants it in rectangular, though. So he's being a dirty dog. He wants me to finish this up and say, well, what is the cosine of 480? Well, 480, go all the way around the circle. That's 360. So how many is left to get to 480? I believe it'd be another 120. 360 plus 120. 120 is down here. So technically, I'm dealing with a 120-degree angle, which is coterminal with the 480. They operate the same way. But I need the reference angle here. That reference angle that I'm going to play with would be whatever from 180 to 180. Wait, I messed up. 120 is not down there. Hello, Cartwright, get it together. That here's my. It was 360, and then it stops. It stopped where? Here, up here, it stopped. So this is my 120, which acts like 480. This is my reference angle. Okay, so 180 minus 120 is 60. So I found my angle to be reference angle to be 60 degrees. Okay, so if I was to draw a triangle with a 60-degree angle, this would be my 1, this would be my 2, this would be my square root of 3, because the 1 is always across from the 30. There's my right angle. So what is the cosine of a 60-degree angle? Cosine of 60 is adjacent 1 over 2. It's a half. But remember, in this quadrant 2, this value down here, which I call it a 1, is negative 1. Cosine's negative in quadrant 2. So 256 times negative 1/2. What am I doing here? Yeah. 256 to the 1/2 plus I, the sine of this reference angle, which is opposite over, and sine is positive square root of 3 over 2. Well, if I distribute that 256 in, because it was on the outside of both of those, it is on the outside of that whole problem. Half of 256 is 128. And then the 256, it actually, you know what? What I should have said was it's half of each, so technically it's a 128 on the outside with a negative 1 plus I square root of 3, because the 2 both cancel by changing that 250 to 128. And if you want, you could actually pull out a negative and call it a negative 128, 1 minus I square root of 3. I kind of like that answer better. But if you want to keep that negative, you can just keep it positive. You can do either answer. Let's see what he has. Get another screen. Nope. Okay. Look at all that work. Holy cow. I see a lot of the same words I said. Okay. Yeah. I pulled out the negative, and I think he messed up, because he pulled out this negative. Oh, no, no. All he did was he distributed in. Okay, fine. That works too. That'll give you the same answer as I had. If I pull out the negative 128, that would give me a 1 minus I square root of 3. We agree. A lot of ways to write your answers. Wow, that was fun. Now, this is where you got to hold on to your seatbelts. He's talking about the nth root. Nth root means the power that goes outside. Like if I say nth root of x, and if I say n is 2, then it's a square root of x, or x to the half. If I say cube root, then that would be the nth root was a 3. Cube root of x, that would be x to the 1/3, cube root. Like cube root of 8 is 2. So we're talking about that index right there. That's an index. What number, in square root, you may not think about it, but it really is an invisible index of 2. Okay? So he's coming up with, you can take a complex number to an nth power, nth root. Nth root means this number that's inside here. And you can rewrite it as a different complex number, known as the nth root of the complex number. And we're going to use another formula from Moivre. So if n is any positive integer, and r is a positive real number, because remember you have r and you're going to be outside of cis of some theta, then the non-zero complex number, r cosine theta plus r plus I sine of theta, that's just a complex number, has exactly n distinct nth roots. So whatever root you have, like square root, cube root, it has n distinct roots given by this formula. The nth root of r, cosine of a different angle, not theta. We started out with theta. This is not theta. This is a different angle that we're going to have to find. So you're taking the nth root of r, or the nth root of r cis of a new angle. Now this new angle, very confusing. Since you have n distinct roots, there are more than one answer. Square root has two roots, plus and minus. Cube root technically has three roots, but we only think of the real ones. How do we find that new angle? It's your original angle plus or minus 360 degrees, or 2 pi if you're in radians, times some factor called k. I'll get to what k is in a minute, divided by whatever that nth root was. So if it's a square root, n is 2. If it's cube root, n is 3. If it's the eighth root, n is 8. Now, if you want to break this up, make it simpler to see, it's theta over n. Take your angle over n, like my theta was 60 degrees over 3. And then you got your next one is plus or minus 360 times some k over n. Now k is the number of roots. K, if you have a cube root, then you can have up to, cube root means 3 minus 1, you'd have 2 of them. You'd go all the way to 3 minus 1 is 2. So 1, 2, 3, there's your cube root. Square root, you would have k is 0, k is 1. Eighth root, k is 0, k is 1, k is 2, k is 3, k is 4, k is 5, k is 7, all the way to 7, 5, 6, 7. This gets confusing. I'll refer back to this chart again. So a reminder of what we just had, this formula that he just gave us. Note, in a statement, the nth root theorem, if theta is in radians, you'd use 2 pi instead of 360. Fine. I'm leaving this here. I keep putting this back because I just want to keep referring back to this formula. Find the 2 square roots of 4i. Write the roots in rectangular form. So what he's saying is it's square root, so the index is a 2. So what I'm doing is I'm finding the square root of 4i. Well, you've never taken the square root of an I number before. Well, you know that the square root, actually you have. The square root of a -1 is I, but you've never done the square root of I. Okay? So we're doing something a little different now. We're doing the square root of 4i. And he wants the answer in rectangular form. So first of all, let's take 4i, which, by the way, a plus bi, that would be 0 plus 4i, is my complex number. That is a complex number. Write it in trig form. So if I have 0 plus 4i, complex form, let me draw out my triangle here. Go 0 left and right, but go up 4. It's this vector here. It's that vector here. So what's the angle of that vector? What's the angle between the 0 degrees here? Well, that's 90 degrees. So I'm going to say pi over 2. Theta is pi over 2. I'm going to be very fancy. Well, how do I find the argument? Remember the square root of, in other words, how long is r? Square root of 0 squared is 0. And 4 squared is 16. Square root of 16 is 4. Well, duh. Look at it. It's 4. I can count it. So So 4 cosine of pi over 2 plus I sine of pi over 2. There's my trigonometric form for this is equal to 0 plus 4i, but in trig. All right. I kept this on many pages, so I think I put several here. I wrote this out again. What did I do now? Okay, I'm checking my work. Yes, I got that right. Now the square root, I already found that the square roots have an absolute value of square root of 4 is 2. So where did that come from? What he's talking about is here. You take the nth root of my r. So the square root of my r, which is the square root of my 4, is a 2. So there it is. Now, I need a new angle. This is my theta. But remember what we had on the other page? My new angle, he's calling it alpha. Remember what it was? It was my theta divided by n. Theta divided by n is what we had. Plus 360 degrees times k, also divided by n. So when I divide my theta by my angle, which was pi over 2 divided by 2 gives me pi over 4, plus 2 pi that I had divided by 2 times k, because there's going to be, you're going to find out we're going to have, how many k's am I going to use? I'm going to need 2. So this simplifies to pi over 4 plus pi k's. So hold that thought. What do I do with that? Don't forget we have the 2. Don't forget I have this now. We're trying to find alphas. Next screen. Reminder again. We're correct on this. We've got our theta, we got our r, and here's my last step I just did. There's my alphas. Okay, next step. At the very beginning, he said write the roots in rectangular. Doggone it. And I'm repeating, I don't know, I repeated the problem again, why I did that. Since there are 2 square roots, why? Because n is 2. Let k be 0 and 1. So in my equation that I gave you a few minutes ago, but I simplified it, if you remember, I simplified it for pi over 4 plus pi k. I'm going to plug k to be 0 and k to be 1, because square root is the index of 2. So I need to use 2. If k is 0, then 0 times pi is 0. That leaves me just with a pi over 4. So there is pi over 4. If k is 1, look at it. Pi over 4 plus 1 times pi is pi. So there's I have pi over 4 plus 1 times pi. Well, put that into one fraction. That's the same thing as pi over 4 plus 4 pi over 4. That's 5 pi over 4. So there's my other one. Okay. So, using the formula, we're going to write out both of our answers. Dirty dog, what do you... So, I don't know why I did that. If k is 0, I have 5 pi over 4. If k is 1, I have 5 pi over 4. And here I go, plug it all in. I have 2 cis of, well, actually, let's write it out. One answer would be 2 times cosine of pi over 4 plus I sine of pi over 4. There's one of my roots. One of my roots. Since it was a square root, I have the second one. 2 times cosine of 5 pi over 4 plus I times sine of 5 pi over 4. He abbreviated both of them. Why not? That's a lot less writing. Look at how much ink I just wasted. I should have just said equals to 2 cis of pi over 4 equals to 2 cis of 5 pi over 4. I tried making some arrows for you. Oh, that was my formula. Taking these two as my angles and plugging them into here to get the two answers, which is what I did to get both of those. I don't know. Maybe I made it more confusing. I'm. You should have already looked at the video that I sent you for somebody else to teach this lesson, because I think that would have given you a good perspective. Remember what he said back? He wants me to take these two answers and convert them into rectangular. In other words, I don't want any trig in there. Here goes. Well, that's not hard. Pi over 4 angle. That's right here. 45, 45, 90. 1, 1 square root of 2. What's the cosine of a 45? You're right. 1 over the square root of 2. What's the sine of 45 degrees? You're right. Opposite over hypotenuse. It's the same thing. So that turns into 2 times, what'd you say it was? 1 over the square root of 2 plus I times 1 over the square root of 2. But you know our book does not leave radicals in the bottom, so that's 2 times square root of 2 over 2 plus I times square root of 2 over 2, and therefore this 2 distributes and you cancel it, so you're left with one of my answers will just be square root of 2 plus I square root of 2. One of your answers. Let's do the second answer. 5 pi over 4. 1, 2, 3, 4. I'm down here. And again, it's a 45-degree reference angle, so that's a 1, but it's a negative 1. That's a 1, that's a negative 1. That's the square root of 2. So what's the cosine of 5 pi over 4? Well, adjacent over hypotenuse. Negative 1 over square root of 2. Or negative square root of 2 over 2. What's the sine? The same thing. Sine of 5 pi over 4 is negative square root of 2 over 2. So now when I write that one out, and I go and write, I'm using this one right here, that's 2 times a negative 2 square roots of 2 plus or minus I negative square root of 2 over 2. Distribute the 2, the bottoms cancel. You're left with negative square root of 2 minus an I square root of 2. There's your second one. So you just found the square root of, what was my original problem? Oh, it was 4i, wasn't it? Wow, that's very simple. But look how much work it was. Let's see if we're right. Yes. Oh, we didn't finish the problem. 2 plus I squared is a 2, negative 2 minus 2. Do I have the negative 2? Woof! Now, I like... Okay, we're on example 3. Find all the fourth roots of negative 8 plus 8i square root of 3. So what we're looking for is the fourth roots of this complex number, negative 8 plus 8i square roots of 3. Don't you wish your calculator could do that? Don't you wish you could do negative 8 plus 8i square root of 3 raised to the 0.25 power. Try it out. Anyway, first thing we do is write this in trigonometric form. So this starts out as 8 on the real number part. So this is negative 8 down here, over there. Then I got to go up 8 square roots of 3 up. 8 square roots of 3 up is it's almost a 16. It's really high. So let me just draw my complex number about here, and then if I label my triangles, this was negative 8, and this is 8 square roots of 3 distance, because that's my I distance. Remember, this is my I, and this is my A. And I graphed a negative A, 8 for A, and then this is my B. To turn this in trigonometric form, need this R, and I need this theta. Okay? So let me do R first. That might be the easiest. Square root negative 8 squared plus 8 square roots of 3 squared. R is square root positive 64. Now 8 square roots of 3 times 8 square roots of 3 is going to be 8 square roots of 3 times 8 square roots of 3 is 8 times 8 is 64. Square root of 3 times square root of 3 is square root of 9, which is another 3. 64 times 3 is 192. So R is equal to square root of 64 plus 192. R equals the square root of, what do those add up to? 6 and 256. What's the square root of 256? That is, R is 16. R is 16. 16 times 16 is 256. Feel free to use your calculator. Now, let me get theta. Theta is my y over x, or my opposite over adjacent. 8 square roots of 3 over negative 8. The 8's cancel, leaving a negative square root of 3 over 1. Those are familiar numbers. Those comes from here's theta. One of the sides has to be square root of 3, and one of the sides has to be a 1. Third one, 2 times cosine of, and it was 210, plus I sine of 210. Next one, last one I think, 2 cosine of 300 degrees plus I sine of 300 degrees. And I believe in the problem he wanted us to write all the roots in rectangular. So, being the usual dirty dog that he is, these answers aren't good enough for him. He wants me to actually evaluate each of these trig functions. So think about what we have here. 30 is easy. 30 is easy. 1, 2, square root of 3. We can do the cosine and sine very easily. 2 cosine of this 30 is square root of 3 over 2. Plus, I don't know why I put a parenthesis there. Trigonometric form with my eraser. I should do those in blue. 2 square root of 3 plus I times the sine, 1/2. Notice what happens when you distribute the 2. You get a square root of 3 plus an I. Do the second one here. 2. Now when I do a 120, all that means now is that my reference angle now is in quadrant 2. This is still a 30-degree angle, but my square root of 3 becomes negative now. So when I'm looking at this triangle now, I'm in quadrant 2. So 2, the cosine of this is negative square root of 3 over 2 plus I times a half. And if I distribute the 2 again, I get now a negative square root of 3 plus an I. Third one, right here I am, 2. Now I'm at 210 degree. Same picture, but now I'm down here, and my 30-degree angle is there. So if that's still 30, now this is a negative 1, this is a 2, this is a negative square root of 3. So both x and y change sign. So cosine is still square root of 3 over 2, but one of them is negative. Negative square root of 3 over 2, just like in quadrant 2, plus I times a negative 1 over 2. So what happens now when I distribute? I've got a negative square root of 3 plus I over 2. No, the 2 canceled. Plus I. Last one. I'm in the 300 degrees. This is over here. This is still a reference angle of 30. Am I wrong in all my angles? 30. 120. Yeah, it's a 300. My reference angle changed. It's a 60 here. Reference angle is 60. The rest were all 30s. They were all a difference of 30 degrees from the x-axis, but this one now is a difference of 60 degrees. So yeah, I almost made a mistake. So now my triangle changes, because no longer is this a 1 now. 1 would be here, and this would be my 2, and this would be my square root of 3 being negative here. So that turns into 2 cosine of this angle, 60, in quadrant 4 would be 1/2. Sine, on the other hand, would be the opposite, negative square root of 3 over 2. Distribute the 2, and I get a 1 minus square root of 3i. Some people like to write it as 1 minus I square root of 3. So there's all 4 answers. And I liked them in this answer, because that was just in trigonometric form. I was already done, but he wanted them in rectangular form. Wow. Have fun with that. Double check all the math, make sure. Positive. I lost that negative right here. That was a negative 1/2, remember? So that's a minus. And this also was minus, if you recall. So that one's fine. Okay. So I think they're okay now. Doesn't hurt to keep double checking. Let's see. One of these is wrong. Square root of 3 plus I. Oh, maybe it was the second one. Let me look at the second one. 120 was here. 120 minus 30 is 1. 50. 1, 2 square root of 3, cosine. There's my problem. The 60-degree angle struck again. That was 60. Well, I mean, it was 100 and... It is 120 degree, but that was reference angles of 60. Ah, darn it. So I switched this to be a square root of 3 here, and this to be a 1 here, and the ones that, okay, that does change that answer. That changes it to, let me erase. It's only human. At least we're finding it, or I'm finding it. Somebody would have called me and told me cosine is negative half. Sine is square root of 3 over 2. That changes this to a negative 1 plus square root of 3i. Or I square root of 3. Okay. Let's check the king, the author. There's my alpha formula using 4Ks, 30, 120, 210, 300. He wrote them in trigonometric form, abbreviated. Looks good. There's all of his work. Wow, see, that's the same thing I had. That's the one I had made a mistake on, and I fixed it. There it is. Okay, I think they're good. You double check it. I don't want to look at it no more. It's making me sick. Example 8, 3. Oh, that's the same problem I just did. Same problem. Go ahead and compare the answers. They're the same. Doesn't look any different on this page. We'll take a look at the solutions graphically. Look at it. Looks real pretty. Got your 30. Then we had to do the 120. So that was 120. That makes that a 60-degree angle. Then we had 210 down here, where that's another 60-degree angle. And then we did another 60-degree angle, another 60-degree angle if you go from all the way to that 30. These are all, let me make sure, 300. That was 60. Actually, they're all 90. I'm sorry, they're all 90 in here. It was 30 to here, 60 to here, 30 to here, 60 to here, 60 to here, 30 to here. They're all 90. They're all at right angles. It's really interesting how if you graph the trigonometric form. Example 4, find all complex number solutions of x to the 5th minus 1 equals 0. Graph all these vectors in the complex plane. And you'll notice I have a right over here. I thought he had a mistake. I was thinking there wouldn't be 5 complex. I'll give you a reason why I wasn't thinking so. I know I'm wrong now because I'm thinking about my x to the 5th minus 1. If x to the 5th minus 1 was indeed 0, that makes x to the 5th equals to 1. That means if I do the 5th root of both sides, the 5th root of both sides, I get x is 1. So I was thinking, oh, that's a real root. Yeah, that is the only real root there is. So there should only be 4 complex. But technically, all real numbers are complex because if x is 1, that vector looks like this. 1 is my real part, there's my a, plus 0, I, There's my B. So it is complex. All real numbers are complex. Not all complex numbers are real. So that means there's 4 left. So there's 4 pure complex and 1 that is real. So it is a total of 5. So I jumped the gun there when I was looking at this. Now, what does that vector look like? 1 plus 0i means 1 to the right, so 1 to the right, and do not go up or down, so the vector stops there. So that vector has a length of 1, so r is 1. And the degrees that I make when I'm at 0 degrees and I haven't moved, theta is 0 degrees. So it's not a surprise to realize that 1 is equal to a 1, there's my r, times my cosine of 0 degrees plus I sine of 0 degrees. There's my first trigonometric form of my first vector. Now we got to do the rest of these. So what I think I'm going to do is I'm going to go to a blank page. I think I still have it. Did I write it down? No, I haven't written it down. And remember that I'm starting out with x to the 5th minus 1 is 0. Therefore, x equals to 1. And my first root that I found was indeed, in trigonometric form, was 1 times sine of 0 plus 0 times, I messed up. This is cosine. Let me fix it before somebody gets mad. I'm sure somebody will get mad. Can't erase it. Won't let me erase. Come on, erase it. There it goes. I'm trying to hide the evidence. Cosine of 0 plus 0 sine of 0. So there's my first trigonometric form. Now, we had a formula back here. We wrote a formula that and there's my same formula for alpha. There's my complex number in trigonometric form. Here is k is 0, 1, 2, 3, and 4. He abbreviated every one of them to be cis, which is a lot less writing. So I like that. So there's the picture. He converted it back to non-cis. There's all 5 of them.